see, we're going to look at complex numbers today.
He's working on your practice in the LOL.
That'll be all right.
Just getting an understanding of that before he goes.
Complex numbers. It kind of means imaginary numbers. Has at least one component of our complex number. And I don't mean just imagining a number. That's not what we're talking about with imaginary numbers. So PSAT tomorrow, sophomores and juniors, PSAT training, testing at your home campuses. So we will not have B-Day classes since everyone's testing. Thursday there's like a field trip in Mr. Price's class, and there's the end of quarter celebration party up here from like 1 to 3. So we're not moving Tuesday classes to Thursday either. We're just having all B-Day classes be asynchronous, which means you don't have to come to class on Tuesday, and it's not going to change it to Thursday or Friday. So you should have your assignments and your B-Day classes in your Google Classroom, and you could do. All right, everyone. We've got plenty of folks in here. Let's go ahead and pull up. Let's see, where am I at? Okay, going to our grade screen as usual. We scroll down. We know we're through Module 1. We're getting close to finish with Module 2. This week we have the complex numbers and operations on complex numbers. So we're going to learn about complex numbers and how to do things with them. 2.06, 2.07. That's the two things due this week. Next week we'll have polynomials and then our practice test. So just one lesson next week with the practice test, which means the test is not far behind. In my class, I give you to the end of the second module to turn in everything from the first module. So if you're missing anything in the first module, you've got about 2 weeks to get it turned in. It depends on the teacher. Some teachers may have a 2-week deadline or something like that. I give you another module. So like if you're missing this test, you need to have it by the time we take the next test. So, but yeah, teacher by teacher determines when you can turn in late work. So you're still good in here if you're still missing module 1, but we're getting closer. So if you're still missing, some of you haven't turned in part 2 of the test. You need to get that done soon. Don't keep dragging it out. Besides the fact you're going to forget all this stuff because we're working on different stuff now. All right, let's go look at our lessons this week, 2.06 and 7, complex numbers. In this lesson, you'll be learning about a new type of number, the complex number. But in order to understand complex numbers, you must understand imaginary numbers, which may also be new to you or maybe not. So to distinguish imaginary numbers from other types of numbers, we got to review what these other types of numbers are. So we're going to learn what causes the need for imaginary numbers and what types of parts are necessary for complex numbers. So let's look at the classification of real numbers first. If we're talking about imaginary numbers, let's see what the real numbers are. So there are the natural numbers. That is what we commonly call the counting numbers. It's like if I threw a bunch of items on the floor and said count those would be the natural numbers. 1, 2, 3, 4, 5, 6, 7, 8. Right? 0 is not included. We add that when we get to the whole numbers. Whole numbers are 0 plus the natural numbers. 0, 1, 2, 3, 4, 5, 6. Integers include everything above, all the whole numbers and all the natural numbers, but it also adds the negative whole numbers. Right? -2, -1, 0, 1, 2. Those are all integers. Rational numbers are any number that can be expressed with a fraction. So that includes integers, whole numbers, and natural numbers. But rational numbers also include like -3/4 or +2/3 or anything. You know, even like I say, integers are included because we could express 4 as 4/1 as a rational number, as a fraction, 4/1. But any numbers like that, all integers included, all fractional values. And then finally, the irrational numbers. That's any number that's basically not a rational number. You can't express it as a fraction. This includes all decimal values that do not repeat or terminate. So any decimal you have that just goes on and on and on forever without repeating is an irrational number. Like pi is an irrational number. The square root of 2 is a rational number. 3.12428583617 dot is an irrational number. So any real number that doesn't fit into any of the other four categories are irrational numbers. And some numbers may fall into more than one category. So make sure you did them all. So for each of the following, decide which kind of number it belongs. So 5 is a natural number, normal counting. 0 is not a natural number because the natural numbers are only the things like counting something. If you have a little kid, count how many toys they have. They would not ever use -3. They would never use 0 because kids don't count with 0. The natural numbers are only the positive integers. 2/3, -1/7. All of these are not natural numbers. Pi, 2.7. See, 5 is the only natural number in there. But if we include whole numbers, okay, 5 is included in that. 0 is included with whole numbers. -3, no. 2/3, no. -1/7, no. Square root of 3, pi, 2.7. So we only add 0 to the natural numbers to get the whole numbers. The integers include anything that's a whole number, positive or negative, but not fractions, not square root numbers that are not integers, pi, 2.773. Then we get to rational numbers. That includes all of what we've already had, plus anything we can express as a fraction. This is not a fraction. This is not a fraction. This cannot be a fraction because it keeps repeating dot, 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 dot. But then, oh, it starts over. So there we go. And there's a little graphic that shows the whole thing. The natural numbers are included inside the whole numbers, which are included inside the integers, which are included inside the rational numbers. Then you have the irrational numbers that are separate, and they do not overlap. No overlap. So that's just a nice review of our number system. So, imaginary numbers. What pairs of identical factors will produce -1 when multiplied? Ah, that's a good question. That's a good question. So I'm going to pull up some notes and get started on this. Let's start with some notes. It wants to know what two numbers we could multiply together that would equal -1. And this is what led to the need to create imaginary numbers, because sometimes in doing some high level math, you need to work with some numbers and some things that just don't naturally come to mind. 1 times -1. I'm talking about the same number. Let's do it this way. X times X. I should change this to an asterisk or something so it doesn't look like it's another X. What number can I multiply by itself to get -1? Because you're right, we can multiply 1 times -1. But if I want the same number and I want to end up with a -1, we kind of run into a problem. Because if I multiply 1 times 1, I get a +1. And if I multiply -1 times -1, I still get a +1. And any other numbers I use won't give me a 1. So I won't end up with a -1. So this led to the need to figure out a number that we could multiply by itself to get to -1. And so that number is the square root of -1. Because if we multiply the square root of -1 times the square root of -1, it's that, because we're taking the square root of -1 and squaring it. And when you square something that's a square root, it just cancels out the square root and becomes -1. So this is an imaginary number. And we've given this specific imaginary number a name. The square root of negative 1 equals I. I. So when we put I into an equation, that's the same thing as the square root of negative 1. Imaginary number. I equals the square root of negative 1. I is a number in math, just like E is a number in math. There's certain letters that we have designated values for. So we're starting our notes with I. So 1 times 1 doesn't work. Negative 1 times negative 1 doesn't work. 1 times negative 1 does that, but they're not identical factors. So the concept of the imaginary number was invented to solve this problem. And it was defined as I, and it equals the square root of negative 1. So with this definition, the square root of negative radicands in addition to positive radicands may be simplified. Here's some more on the history of the imaginary number. We won't spend long on this. We got a lot to cover. This says, up to this point in your math education, you've been working with numbers in the real number system. But you're about to discover there are numbers not included in the real number system. These are called complex numbers. And what makes these numbers special is the existence of imaginary numbers. And you may be thinking, why do I need to know about these numbers if they don't exist? Well, they do exist, and the term imaginary is generally thought of as an unfortunate title for them. So secondly, why do you need to know about numbers at all? Well, throughout history, there's been times when a mathematical construct was invented before they knew a purpose for it. Like early man knew the concept of 1, but did not know anything about 0. We discovered the natural number first, 1, 2, 3, 4, 5, but had no concept about the number 0. Because numbers at the time were used to count sheep or count other animals as a source of food, and there was no need to define the concept of 0. Well, there's nothing to count. How many sheep do you have? Well, there's nothing to count. You wouldn't say you had 0 sheep. You just say, I don't have anything to count. When fractions were first defined, they were thought of as useless. What purpose could there be having a number between 0 and 1? You either have a sheep or you don't. Today, we use fractions all the time with food ingredients, counting money, telling time, everything. So the concept of imaginary numbers has a similar history because they got to where they were trying to solve an equation like x squared minus 9 equals 0, and they could do that, right? Add 9 to both sides, x squared equals 9. And since x squared equals 9, the answer is either 3 or negative 3. That was great. We could do that. But then they said, what about x squared plus 1? Well, that became a problem. You subtract 1 from both sides. Now you got x squared equals negative 1. So taking the square root of that ran into a difficulty. Wait a minute. Square root of negative 1, we can't really do that. So they invented I to solve that problem, even if they didn't really know what it was good for at the time. So simplifying an imaginary number. Let's try to simplify the square root of negative 4. So the square root of negative 4 is the same as the square root of negative 1 times 4. And we'll use this a lot. Which that means we can just change this to an I. I square roots of 4. Because that's what we call the square root of negative 1. It's just I. So I square roots of 4. And we know what the square root of 4 is. It's 2. So the solution to the square root of negative 4 is 2i. 2i, because I is the square root of negative 1. So, all right. But isn't I a variable? Oh. Please note the distinction between the variable I and the imaginary I. For the purposes of this course, imaginary numbers will be written in italics. All right, so we make that an italic I, where if you're using I as a variable, it'll be in the normal font. But we rarely, if ever, use I as a variable because we don't want it confused with the square root of negative 1, the other I. All right, we're going to watch this video.
In this problem, you are asked to simplify the square root of negative 8. Begin by factoring the imaginary number from the radical. Rewrite the square root of negative 8 as the square root of negative 1 times the square root of 8. The square root of negative 1 is equal to I, so you can rewrite this as I times the square root of 8. Since the square root of 8 is not in simplest form, rewrite it as a product of its perfect square factor, 4 and 2. So now you have the product of I times the square root of 4 multiplied by the square root of 2. Now you can simplify the square root of 4 as 2. Like coefficients of variables, typically the whole number is written before I, so the final simplified expression is written as 2i times the square root of 2.
That's how that works. When you have the square root of a negative number, you pull out the square root of negative 1 and convert it to an I. Then you deal with simplifying the radical. 8 can be the same as 4 times 2, so we can take the square root of 4. And then, as he said, we generally always write the number in front of I, just like we write the number in front of a variable. We'd say 2x, not x2 in general things. So the same thing works with I. Simplify the square root of negative 45. So let's do that on paper just to get some notes going here again. Let me switch over here. The square root of negative 45. So if we want to take the square root of a negative number, the first thing we'll do is pull out the negative 1 and the 45. Pull them, make it separately. Which you can separate whatever's underneath there just by taking the factors that multiply to be that. So this means this is I times the square root of 45. Now 45 is not in its simplest form because we know that we can pull a square root out of that if we separate it to the square root of 9 times the square root of 5. Because we can take the square root of 9. So this would be the same as 3i square roots of 5. And that would be the simplest form of the square root of negative 45. You just break it up piece by piece. Always pull the I out there first. And then you can break down the number into whichever numbers you can simplify that into. So I get our notes going a little bit. This is right here also in the lesson. Check the answer. And you take first, pull the square root out where it's I square root of 45. And then to simplify that further, 45 is the same as 9 times 5. Square root of 9 is 3i. And notice when simplifying, we always assume the positive, right? We talked about that last week. Assume the positive, because also it could be negative 3, right? Negative 3i. We always just take the positive value when we're simplifying these. Page 2. That was a lot on page 1. All right, you're doing great. Let's take a look at what happens to the imaginary I when it's raised to a power. Oh, this is good stuff. All right, we're going to put this on our notes as well because we need to understand this. So I is the square root of negative 1. We've learned that. That one's pretty easy. We've got that. We just have to memorize that one. What about I squared? I squared is the square root of negative 1 squared, which means these cancel each other out. So I squared equals a negative 1. No square root, just the number negative 1, because it's negative 1 times the square root of negative 1 times the square root of negative 1, which is just negative 1. How about I to the third power? Well, that is negative 1 squared times another square root of negative 1. Right? I could break it out the third to be a squared and a 1. And we know that this equals negative 1, so it's just negative 1 times the square root of negative 1, which means it's just the negative square root of negative 1, or negative I.
You can take a picture too, so we feel perfect.
If we just continue it out. Third power, it's the second power times the first power. We know the second power equals -1, so it's -1 times that, -1, which is just negative times the squared I. So it's just negative I. That's what it equals. And we'll highlight that in a moment. I to the fourth power is the square root of -1 squared times the square root of -1 squared, right? We can break it out fourth power to the squared times the squared, which means it's -1 times -1, or a +1. So let's kind of highlight this, keep this out. I equals the square root of -1. I squared is -1. I to the third is negative I. I to the fourth is just 1. Now here's what's really cool. If we want to know what is I to the 26th power, you're like, oh my goodness, that's going to take a while because we're only to the fourth power, and this is getting longer and longer. Well, let's look at this. I to the fifth power. Let's go one more right here. I to the fifth. Well, that's really the same as I to the fourth times I to the first. Because if you remember our exponent properties that we looked at last week, and the week before, you can add those together, the product property. Like x to the seventh is the same as x to the 3 plus x to the 4. So x to the 5 is the same as 4 plus 1. We can break these back apart as a 4 plus 1. And we know what I to the fourth is. I to the fourth is 1. So this is 1 times I, or just I. 1 times I is just I. Wait a minute. That's just square root of -1. That's the same thing as I to the first. Well, what about I to the sixth? Well, that's I to the fourth times I squared. I to the fourth is just 1. I squared is -1. So that just equals -1 because I squared is -1. And I to the seventh is I to the fourth times I to the third. I to the fourth is 1. I to the third is -I. So it just equals -I. What I'm seeing is this is just repeating, which means we can already guess that I to the eighth is just going to equal 1 because it's I to the fourth times I to the fourth. It's 1 times 1. So this repeats every 4, every 4, every 4. Going to repeat, 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 repeat. So 26 divided by 4, for how many times does it repeat? Well, that would be 24 with a remainder of 2. Not 24. It'd be 6. But I mean, 4 times 6, it would go to the 24. Goes in there 6 times with a remainder of 2. So that means it equals -1. Oh, this week. This is -1. I to the 26 is -1. Because let's go I to the first, second, third, fourth, fifth, sixth, seventh, eighth, ninth, 10th, 11th, 12th, 13th, 14th, 15th, 16th, 17th, 18th, 19th, 20, to 1, to 2, to 3, to 4, 25. The 26th. I to the 26th is -1. So if you know these 4, have these 4 in your notes, what they equal. This is negative square root of -1. If you know what those 4 equal, then you know what this equals, and you know what I to the 31st equals, and I to the 17th equals, and I to the 40th equals, because it just keeps repeating. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So you should have this in your notes and an explanation of how to find anything bigger, however that makes sense to you. See, I did the 5, 6, 7, 8 just to continue the pattern. 1, 2, 3, 4, 5, 6, 7, 8. And it will talk about this in our lesson as well. If this maybe this makes more sense to you. Let's see. Did you know that I equals the square root of negative 1? So I squared is the square root of negative 1 squared, and that's going to equal negative 1 because if we took 3 squared, the square root of 3 squared, that's the same as the square root of 3 times the square root of 3, which is the square root of 9, which is just a 3, because those cancel each other out when you square something and take a square root. So that same concept tells us squaring something and square root will cancel those out, and it's just a negative 1. So I squared equals negative 1 is a very important definition when we're working with imaginary numbers. So we make sure you keep this very handy. That needs to be in your notes. I squared equals negative 1. I to the third equals negative I. And they break it down like I did. I to the third is I times I times I. I times I is I squared, which is negative 1. So it's negative 1 times I, or negative I. I to the fourth, I times I times I times I. It's I squared times I squared. It's negative 1 times negative 1. It's just a positive 1. I to the fourth is. So then they talk about what will I to the fifth be, and they show that it equals I. And so they're showing, here's the first 16. I squared, I the third, I the fourth, I the fifth, I the sixth, I the seventh, I the eighth, ninth, 10th, 11th, 12th, 13th, 14th, 15th, 16th. And you can see all of these equal I, all of these equal negative 1, all of these equal negative I, all these equal 1. So maybe this in your notes may help you understand that better, but you can just keep that table going, right? Just keep it going 4 at a time. Fortunately, you won't need to memorize all the higher exponents of the imaginary number, but it will help if you remember that the first 4 exponents of I. If you remember these, you can simplify to any power by first dividing the exponent by 4. Figure out what the remainder is. If there's no remainder, that means it equals 1 because it's evenly divisible by 4. So they have another example, I to the 27th. Well, if you divide it by 4, is that the one I did? I did 26. It will go into it 6 times with the remainder of 3. So then you would be the same as I to the third. The remainder of 3 is negative I. If you want to look at the 34th, divide that by 4. What's the remainder? The remainder is 2. So I squared is negative 1. So it's going to be the same as I squared because the remainder is 2. I to the 40th, the remainder is 0. So that means it's going to be equal to I to the fourth, which is 1. Or I to the 0, which is 1 as well. All right, page 3. So a complex number. We've been wanting to know about a complex number all along. That was the title of our lesson. So let's put what a complex number is in our notes. A complex number could be something like 10 plus 7i. Ten is the real part. That's a real number. 10 is the real part of the complex number. The complex numbers also have an imaginary part. So that's the imaginary part. This is the real part. Complex numbers. So all complex numbers have a real part and an imaginary part. Now understand, sometimes the real part may be 0. you may see an imaginary number that's just negative 2i. Well, that means that the real number was just a 0 and we didn't put it. 0 minus 2i. So they just list negative 2i as the imaginary part. But complex numbers have to have a real and an imaginary, even though the real could be 0. Now, if the imaginary doesn't exist, it's not a complex number. If it's just 10, that's just a real number. So complex numbers have to have an imaginary part, and they might have a real part, or the real part could be 0. But this is the definition of a complex number. You'll have a real part and an imaginary part. But again, the real part could be 0. Real number, imaginary number. They did 7 plus 10i. So complex numbers consist of one term that's a real number and another term that's an imaginary number. So it wants us to divide those up. Okay, which part of these would be real numbers and which would be imaginary numbers? Now this should be as simple as it gets in this unit right here. If it's an imaginary part, it's got I. It's got an imaginary number. 3 is just a number. It's a real number. Negative 6i. When you see that I, that immediately tells you that's the imaginary part. 2, 7i. 5 plus I. 1 minus 10i. 7 plus 8i. Anything that has an I attached to it is imaginary. I for imaginary. Okay, here's our lesson summary for what a complex number is. In our next lesson, we're going to start working with them and doing some math. Complex number, I equals square root of negative 1. Talks about how to simplify square root of negative 45. And then talks about the repeating pattern. I to the first, I squared, I to the third, I to the fourth. And how that'll repeat. I to the 27th equals negative I, because that's the remainder when you divide by 4. So then, again, you can print that out if you have a printer and use this as your notes, or hopefully you wrote this in your notes as we are working through that. Let's see what the practice problems look like. Simplify. Negative 64, the square root of negative 64. Let's go ahead and do just one or two of these practice problems before we move on. This one's a pretty simple one, actually, because this is going to equal the same as the square root of negative 1 times the square root of 64, which the square root of negative 1 is I, and the square root of 64 is 8. That one, we can simplify it to an 8, because the square root of 64. So 6 needs to look more like a 6 there. There we go. So all we have to do is choose the 8i. That's it. And there's 5 of these. Okay, 5 of these. Let's look at the you try 2s. Oh, this is a good one. I to the 5th. Which one of those will they equal? Well, I to the 5th just equals I. That's the first in the category. I squared. I squared is negative 1. I to the 7th. 1, 2, 3, 4, 1, 2, 3. 20th. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. It just equals 1. 13, you divide it by 4, has a remainder of 1. So I'll leave the rest of those for you to try. Let's look at the next page and see what else they have us do. Simplify. Oh, this is just like the square root of 64, except it's a 49. So that's going to be 7. And this is an I, right? 7i. All right. This one we got a little more simplification going. 50 is 25 times 2. And 25, you could take the square root. So it'd be 5i square roots of 2. All right, we're going to move on to the next list. Oh, let's look at what the assignment is. Oh, here's an example. Okay. Conjugates. let's talk a little bit about conjugates first, because that is going to come into play in here. And I added that video because he explains it pretty well too. All right, conjugates of a complex number. If we have 10 minus 2i as a complex number, the conjugate looks very similar. This is the conjugate of that. Conjugates have the exact same real number and the opposite imaginary number. This one had a negative 2i. This one has a positive 2i. If we have 1 plus 6i, its conjugate is 1 minus 6i. One will be positive, one will be negative. But just the imaginary part. These are both positive this time. If we have negative 2 minus I, the conjugate will be negative 2 plus I. Conjugates. If you have negative 8i, you'll have positive 8i. Notice this has 0 as a real part. But this is how conjugates work. This is how conjugates work. And you're like, okay, what's a conjugate used for? What is a conjugate? Well, this is what a conjugate is. And the reason we talk about conjugates is because anytime, if you're doing math and you have a complex number, I've got a complex number here. Sometimes when we do quadratic equations, you could end up using the quadratic formula and you'll have complex number. If you have a complex numbers are very scared. I mean, you think you have anxiety, they have worse anxiety because you'll never, ever, ever find them by themselves. Complex numbers are never by themselves. They always come with a partner, and their partner is their conjugate. So if you're solving a problem and you get 1 plus 6i as an answer, that means automatically 1 minus 6i is also an answer. Guaranteed. Because complex numbers always come in pairs. There's always 2 of them. Never, ever by themselves. And they always come with their conjugate partner. So let's look at this video I have that I've added in here, the conjugate of a complex number, because I had forgotten that I'd even had that in there. I put that in there previous year.
We're asked to find the conjugate of the complex number 7 minus 5i. And what you're going to find in this video is finding the conjugate of a complex number is shockingly easy. It's really the same as this number. I should say be a little bit more particular. It has the same real part. So the conjugate of this is going to have the exact same real part. But its imaginary part is going to have the opposite sign. So instead of having a negative 5i, it will have a positive 5i. So that right there is the complex conjugate of 7 minus 5i. And sometimes the notation for doing that is you'll take 7 minus 5i. If you have 7 minus 5i, and you put a line over it like that, that means I want the conjugate of 7 minus 5i, and that will equal 7 plus 5i. Or sometimes someone will write, you'll see z is the variable that people often use for complex numbers. If z is 7 minus 5i, then they'll say the complex conjugate of z, and you put that line over the z, is going to be 7 plus 5i. Now you're probably saying, okay, fairly straightforward to find a conjugate of a complex number, but what is it good for? And the simplest reason, or the most basic place where this is useful, is when you multiply any complex number times its conjugate, you're going to get a real number. And I want to emphasize, this This right here is the conjugate. 7 plus 5i is the conjugate of 7 minus 5i. But 7 minus 5i is also the conjugate of 7 plus 5i for obvious reasons. If you started with this and you changed the sign of the imaginary part, you would get 7 minus 5i. They're conjugates of each other. But let me show you that when I multiply complex conjugates that I get a real number. So let's multiply 7 minus 5i times 7 plus 5i. And I will do that in blue. 7 minus 5i times 7 plus 5i. And remember, whenever you multiply these expressions, you really just have to multiply every term times each other. You could do the distributive property twice. You could do something like FOIL to remind yourself to multiply every part of this complex number times every part of this complex number. So let's just do it any which way. So you'd have 7 times 7, which is 49. 7 times 5i, which is 7 times 5i, which is 35i. Then you have negative 5i times 7, which is negative 35i. You can see the imaginary part is canceling out. Then you have negative 5i times positive 5i. Well, that's negative 25i squared. And negative 25i squared, remember, I squared is negative 1. So negative 25i squared, let me write this down, negative 5i times 5i is negative 25 times I squared. I squared is negative 1. So negative 25 times negative 1 is positive 25. And these two guys over here cancel out, and we're just left with 49 plus 25. See, 50 plus 25 is 75. So this is just 74. So we are just left with the real number 74. Another way to do it, you don't even have to do all this distributive property. You might just recognize that this looks like this is something plus something times, or something minus something times that same something plus something. And we know this pattern from our early algebra, that a plus b times a minus b is equal to a squared minus b squared, is equal to a difference of squares. And so in this case, a is 7, a squared is 49, and b in this case is 5i. B squared is 5i squared, which is 25i squared, which is negative 25. And we're subtracting that, so it's going to be positive plus 25. You add them together, you get 74.
All right. Might keep handy if you need to come back and review that, because we're going to use a lot of that kind of math in solving complex numbers. All right, let's look at the assignment for 2.06. Simplify square root of negative 121. Simplify the square root of 72. Simplify I to the 38th power. Simplify negative 5 times negative square root of negative 44. Be careful there. There's a lot of negatives you're dealing with. Simplify I to the 12th power. And what is the conjugate of 13 minus 11i? All right, don't make that more difficult. It's a very simple thing to find the conjugate. Don't make that difficult. All right, let's look at 2.07, doing operations on complex numbers. So after learning about imaginary numbers, you may be wondering about their purpose in the real world. While they may be called imaginary numbers, they are anything but imaginary. Applications of complex numbers can be found in the infrastructure of suspension bridges, the design development of airplanes, and most notably in the electricity that surrounds you every day. So we're going to learn how can the associative, commutative, and distributive properties be applied when performing operations on complex numbers. All right, let's talk about adding and subtracting complex numbers. So we can add like, 2x plus 6 and 5x minus 2. If we did that, we got to do the like terms. We'd add 2x plus 5x and get 7x. And we take the 6 and the negative 2 and that plus 4. Right? You got to keep the variables added to the variables and the numbers added to the numbers. Well, complex numbers work very much the same way. Here's a little review on combining like terms. If we had 7x squared plus 3x minus 5 plus 2x squared minus 4x plus 9, you can only combine the 7x squared with the 2x squared because they are both x squareds. You can't add an x to an x squared. Those are not the same. So the 7x squared gets added to 2x squared, and you end up with a 9x squared. The 3x can only be combined with the negative 4x. Those are both x terms. So that ends up negative 1x when we add 3x minus 4x. And then the negative 5 and the plus 9 are just numbers. Numbers can only be combined with other numbers, and we get the plus 4. But that's a little reminder on like terms. So the same thing happens with our imaginary numbers. So let's complex numbers. Let's add these together. Let's add 6 plus 8i to 3 plus 2i. So if we want to add two complex numbers, we have to make sure that we combine the real number with the real number and the imaginary number with the imaginary number. So when we add these together, 6 plus 3 is 9. 8i plus 2i is 10i. That's it. It's that simple. It's very, very simple as long as you don't try to add and say this is 14i. This is not 14i. This is not 5i. You can only add the real numbers to other real numbers. You can only add imaginary numbers to imaginary numbers. And it works the same with subtraction. 6 plus 8i minus 3 plus 2i. 6 minus 3. 8i minus 2i. So we end up with just like terms. 6 minus 3. 8i minus 2i. Subtracting works just like addition. Combine like terms only. Again, this is really simple. You just have to pay attention. Where's the imaginary part? Where's the real part? So they show that 6 plus 3, you bring the 6 and the 3 together because they're both real, and the 8i and the 2i, you get the 9 plus 10i. They're going to do a subtraction problem. So let's see how they do the subtraction. We did one on our notes right there, but let's check out what they're doing.
You've combined expressions many times before, such as when you were combining polynomials and when you were combining radicals. The process for complex numbers is the same. Begin by distributing any coefficients. No integer or variables appear before either set of parentheses. Consequently, an understood 1 is put in its place. When 1 is distributed to the complex number within the first set of parentheses, the parts within are unchanged. However, a negative 1 is being distributed to the complex number within the second set of parentheses. This will change the signs on both the real number and imaginary number which follow. Now you can identify and combine like parts. The 12 and the minus 10 can combine because they're both real numbers, and the 3i and 4i can combine because they're both imaginary numbers. As you can see, combining complex numbers is very similar to adding and subtracting polynomials.
Okay, there you go. You just have to be careful when you're subtracting if there's a negative inside your parentheses. All right, Sophia. So minus a negative 4i, we actually added 4i because it was subtracting a negative. And again, you have this video on page 1 of the 2.07 lesson. Sometimes the complex numbers aren't written this way initially. You may want to convert them from negative radicands into complex numbers for combining. So let's look at this one. This one has another step we need to do first because it looks a little confusing before we add these together. So let's try this.
A lot of students would see this expression and want to add negative 121 and negative 9 right away. But remember, radicals must be simplified into like terms before they may be added or subtracted. That simplification process begins by factoring the imaginary number from all radicals with a negative radicand. Now that the imaginary numbers have been factored, simplify the remaining radicals, if possible. Well, that worked out nicely. All that's left is a real number part and two imaginary terms, which may be combined easily by adding the coefficients.
So that's a very good point. If you would have combined these to start with, you'd have had the square root of negative 130, which is not 14. That would have got you an answer that's totally different and be off. So anytime you see a negative inside your radical there, convert it first to be 11i and 3i, as it is in this case. Negative 121 is 11i, negative 9, 3i. Then you're just adding the 3 and the 11 together to be 14i. And this is actually a lot simpler than if we'd have tried to combine those first, we'd have gotten to a real mess. So that's a very good point. To make sure you rewrite these first before you try combining anything, just to keep you out of problems. So here, we'll try this one on paper. So the first thing we want to do is we want to rewrite anything. And this is 4 times. This is not 4 plus. It's not like this. So 4 times the square root of negative 1 times the square root of 24. So this is 4i starting out. The square root of 24 is the square root of, let's see, what's best? 4 times 6. Because the square root of 4 we can make as a 2. So 4i times 2 times the square root of 6 simplifies to just 8i times the square root of 6. Because these are being multiplied. So we can take 2 times 4i. Right? Or if you went the other way, it'd be 4 times 2i if we did that part first. But so this is 8i square root of 6. And on this one, as we're simplifying, we'll bring that down. This is the square root of negative 1 times the square root of 150. So this is I square roots of 150. Because we converted that I there. The square root of 150, we need to find some numbers that we can pull out of that as a square. Right? So right away I can say, okay, well, that is divisible by 25 because the square root of 25 is 5. So 25 times 6. 25 times 6. So this is 5i square roots of 6. Oh, well, now look at this. Since these are the same, and only because these are the same, we can add these together. If we got 6i square roots of 6 plus 5i square roots of 6, we've got 13i square roots of 6. If these were different, we'd have to leave it. That would be the final answer. If this is the square root of 5 and this is the square root of 6, we'd be done. We can only combine those when they're the same thing. We have 13i square roots of 6. And then we'll double check to make sure our answer matches what they got in there. But I'll leave that up for a second if you're copying down. But it's just breaking apart the pieces. Now, maybe you're thinking, what if I don't know on 150? Let's see. I don't know what the factors of 150 are that's going to be a square. Well, take out the smallest number. You know it's a 2. I can break this down to a 2 and a 75, right? 2 times 75 is 150. Okay. Well, let's see. Then 75 is the same thing as 3 times 25. 25 is 5 times 5. So the factors of 150 are 2 times 3 times 5 times 5. So you've got a 2, a 3, a 5, and a 5. Well, since there's 2 of these together, that's the square root we're looking for. And these, there's only 1, 2, and 1, 3, so we just put those together. 6 square roots of 25. Oh, I'm sorry. Square root of 6 times the square root of 25, because this was the square root to start with. Square root of 6 times square root of 25 is the factors, because it comes down to these are not the same, so they're going to stay underneath there. This gets to come out as a 5, And this has to stay because there's only 1, 2, and 1, 3. But if there's a pair of them, it'll get to come out from underneath there and be just a number because there's a pair of them. When the factors are 2, 3, 5, and 5, and these are all under the square root. Anytime it's got a buddy, it can come out. If it doesn't, it has to stay underneath the radical. So 13i squared is 6. Again, we're going to look and see what their answer is and see how if they stepped it any differently. First, they say factor each one to be 4i square root of 24 plus I square root of 150. So they just pulled the I part out. That's all they did first. 4i square root of 24 and I square root of 150. Then they simplified. So they said, okay, 24 is the same as 4 times 6, and the square root of 4 is 2. So this is 8i square root of 6. This side is 25 times 6. So the square root of 25 is 5, square root of 6. So they get down to the same thing we had, 8i square root of 6 plus 5i square root of 6. Okay. Then, can they be combined? Are they like terms? To combine radicals, the radicands of those radicals must be exactly the same, which they are in this case. Since the factor outside the radical contains an imaginary number, both terms must contain that imaginary number in order to be combined, which they do. So in this one, since we have a square root of 6 in both terms, an imaginary number outside in both terms, we can add them together. 13i square root of 6. Kind of cool. All right, let's go to page 2. Multiplying complex numbers. Multiplying complex numbers. All right, we'll do their example. So they're multiplying the square root of negative 12 times the square root of negative 5. So as they said, pull out the I first, right? Square root of negative 1 times the square root of 12 times the square root of negative 1 times the square root of 5. We just broke all those out, right? 12 is negative 1 times 12. Negative 5 is negative 1 times 5. If we combine these, we've got the square root of negative 1 squared. And we've got the square root of 12 times the square root of 5. Square root of 60. Negative 1 squared. This is I squared. Same thing as I squared, right? Because it's square root of negative 1 squared. We know that just equals negative 1. Times, what can we do with the square root of 60? 60 is, let's see. We know we can take a 2 out of it. 2 times 30. And 30 is 2 times 15. And 15 is 3 times 5. So the factors are 2, 2, 3, and 5. Okay, so this is the square root of 4 times the square root of 15. See, 2 times 2, square root of 4. 3 times 5, 15. We can take the square root of 4. Negative 1 times 2 times the square root of 15. So negative 1 times 2, this is negative 2 square roots of 15. Look, this is a real number. This is no longer imaginary. This is a real number. Square root of 15 is a number, like 3 point something. And we could take 3 point something times negative 2. So the answer is negative like 7 point something. We got a real number answer. And when multiplying two imaginary numbers, that'll happen more often than you imagine. Let's look what they did. So they took negative 1 times 12, negative 1 times 5 as the square roots, which means I squared to 12 times I squared to 5, which is I squared square root of 60, right? And then they showed this, what I was showing, the prime factors. 60 is 2 times 30, 30 is 3 times 10. I did 2 times 15, either way, 2 times 5. So your factors are 2, 2, 3, and 5. You bet, Addison. So the 2's can come out because it's the square root of 4. And 15 stays in. And then you got I squared, square root of 60 gets down to this. 2I squared, 15. 2I squared is negative 1. So our final answer is negative 2 square roots of 15, which we had on our paper. This is a good thing. Let's see what happened if you would have multiplied the radicands first. Like if the first thing you did say, okay, square root of negative 12 times the square root of negative 5. I'm going to say that's the square root of 60 because I just multiplied negative 12 times negative 5. If we had done that first, we'd have come up with 2 square roots of 15, and we'd have missed the negative because the answer was negative 2 square roots of 15. So you have to factor out that imaginary number first, or else you're going to miss the right answer. So you have to factor imaginary numbers before multiplying and substitute all instances of I squared with a negative 1. Now we're going to take it to another level. Oh, is that scary a little bit? Maybe. Let's see. The square root of negative 3 times, and then we have parentheses, 12 plus the square root of negative 6. So we got a couple of I terms in there, and we have a real term, and we have distribution with parentheses. There's a lot going on.
In this problem, you are asked to simplify the square root of negative 3 times 12 plus square root of negative 6. Begin by factoring imaginary numbers. Now distribute the imaginary number outside the radical. Distributing the imaginary number requires multiplying both I and the radical by each part of the complex number within the parentheses. Next, simplify the radicands where possible. Finally, substitute negative 1 for I squared. Can this expression be simplified further? No. Typically, complex numbers are written with the real number part first and the imaginary number part second. You may switch the order of these two parts so long as you take the sign in front along for the ride.
So what they did here is this last step was just reversing it. You had 12I square roots of 3 and negative 3 square roots of 2. And since commonly when you write a complex number, you put the real part first and the imaginary part second. Well, negative 3 square roots of 2, that's a real number. Negative 4.2426, et cetera, et cetera, et cetera. That's what negative 3 square roots of 2 is. It's a real number. It's just irrational. Plus 12I square roots of 3, which is an imaginary number. But it's just distribution. But before they distributed this through the parentheses, they factored out the I, the square root of negative 1. Then after you factor out the I, then it's just normal distributing through the parentheses. All right. Now that you know how to multiply negative radicands, let's take a look at multiplying two complex numbers, because this is where the real meat of it is. This is where we really get into the gravy and why imaginary numbers were created to begin with. Let me write these down because I want to do the same ones they show in your example there. So we have to use the distributive property. We've got to distribute this into that. So 6 times 5 is 30. 6 times 9i, there's an I with that, so this is 54i. Then we distribute the negative 3i into this. Negative 3i times 5 is negative 15i. And negative 3i times positive 9i. Negative 3 times positive 9 is negative 27. I times I is I squared, which means squared. This is the same as negative 27 times negative 1, because I squared equals negative 1. That's where we got to remember that. That is really huge in this whole thing, in making sure we remember when we have I squared, that's going to be negative 1. When we have I to the fourth, that's going to be a positive 1. So we need to simplify those terms to make them real numbers. So this is the same as plus 27. So now let's simplify this. 30 plus 27 is 57. 54i minus 15i. So this is what it equals when you multiply this number times this number. This is the only tricky part. You got to make sure at the end that this I squared is converted to a negative 1, because this is a real number. This is not imaginary number, because I squared equals the very real number negative 1. So this becomes part of the real number answer. The only imaginary parts are left are these two. And they'll show the same thing. Negative 27i squared becomes plus 27. So our answer is the 57 plus 39i. So based on this information, what can be concluded about the product of the multiplication of two distinct complex numbers? When they're multiplied, their product is another complex number that has one real part and one imaginary part. Now with conjugates, and here's our lesson summary, so we're going to get through all this. With conjugates, you got a little bit different situation. And here, we'll just make up our own conjugates to use here. So let's say 4 minus 5i, which means the conjugate is going to be 4 plus 5i. So these two imaginary numbers, two complex numbers, when we multiply them together, let's see what we end up with. 4 times 4 is 16. 4 times positive 5i is positive 20i. All right. Now let's distribute this term. Negative 5i times a positive 4 is negative 20i. Oh, you see this already? This imaginary part's going away. Negative 5i times positive 5i is negative 25i times I squared. Negative 25 times negative 1, because that's I squared is negative 1. So this is plus 25. This is 0. 20i minus 20i. So this is just 41. 16 plus 25. This is the final answer of what you get with these two complex numbers being multiplied together. Imaginary and imaginary, but we end up with real, which is when some higher level mathematicians were doing math and they found that they needed to use imaginary numbers in order to get a very real answer. They started finding reasons that I is a valid mathematical conjugate. Well, it depends on how high in math you get. There are some levels of math where you will end up using this. The normal everyday guy probably won't get to that level. But if you get into engineering, you may use it. In a lot of high technical jobs, you may get into where you need to do some math that you end up with imaginary numbers. But if you're going to make fries at McDonald's or dig ditches, I doubt you'll touch anything like it. Multiplying, there's another example, multiplying the complex number by its conjugate. And again, the imaginary part will go away and you'll end up with just an actual number. Let's look at the lesson summary and then we can look at an example problem or two. Adding and subtracting complex numbers. The only important part to remember is real numbers can only be added to real numbers. Imaginary numbers can only be added to imaginary numbers. Then it gets real easy, as long as you remember that. If a complex number is written as a negative radicand, negative square root of 121, the square root of negative 9, you have to convert those to I terms first, 11i and 3i, before you add those together. Associative property, commutative property, make sure you distribute things properly, multiplying numbers. You distribute, And if you multiply something by its conjugate, you'll end up with a real answer. You won't have an imaginary part at all. Let's look at some of the examples they have over here. Simplify according to the given directions. We have 12 minus 3i plus, we're just adding together, 9 plus 2i. Well, that means the 12 can be added to the 9, and the negative 3i can be added to the positive 2i, which means we have 21 minus i. Great job. The real with the real. There's another addition one. I'll leave those for you to practice on. Let's go look at this. Simplify these, match them with their answers. If we have the square root of 3 times the square root of 7, what's that equivalent to? Well, the square root of 3 is the same as the square root of negative 1 times 3. The square root of negative 1 is I. So you have I times the square root of 3 times the square root of 7. Both of those are the simplest terms they can get, so you can just multiply them together and say that's I square roots of 21. 3 times 7. Same thing. You just pull the I out. That's the part you can simplify. This one, there's an I and an I. So you're going to make this the square root of negative 1 times 6 and the square root of negative 1 times 15. Those will combine, and you can simplify. I'm going to let those go and go to the next page. Because you can do all these practice problems because it will tell you how to do it if you're wrong. So I don't spend quite as much time on these just because it will help you a lot more. Completely simplify these. Correct answer and select submit to see if you're correct. So 2 square roots of negative 50 plus the square root of negative 72. So the second one is going to be I square roots of 72, which you can simplify down because 72 is the same as 36 times 2. 36 is square root of 36 is 6. So you'll have a 6 square roots of 2. Over here, you'll have 25 times 2. So that'll be a 5. So you'll have 10i square roots of 2 plus 6 square roots of 2. So you'll have 16i square roots of 2 when you work that out. All right. There's when you subtract. 1 minus 6, negative 5. Negative 4i minus 9i, negative 13i. Just combine the like terms. There's a multiplication with both negative radicands there. So. All right, let's look at the assignment that goes with this. Oops, I went too far. There it is. Simplify. This one is adding complex numbers. This one is subtracting complex numbers. This one is multiplying complex numbers. This one is multiplying. And this one is multiplying conjugates. Multiplying conjugates. So I hope you know right away those first two answers are wrong because you multiply conjugates, you will get a very real answer. All right, just 5 problems. 5 problems. Simply dealing with complex numbers. All right, if you got questions on this, I will be in class Wednesday. I haven't looked at RTI today, but RTI is put in on Friday. So if you turned in a bunch of stuff over the weekend and got your grade over 70, then I will count you present on Wednesday, even if you're on the RTI list. But if your grade's still below 70 in Buzz, you need to be here Wednesday if you're on the RTI list. So again, we have to put that in on Fridays now. So if you turn in stuff after Friday, RTI may not reflect that. So, all right. Any questions? We looked at a lot today. Play with imaginary numbers, getting into really kind of wild stuff. We're like real mathematicians today, getting into stuff that's just like, whoa, you're hurting my head a little bit there, Mr. Brock. It's all right. Hurting my head a little too. Right there. Right there's a little spot. All right, guys. Have a great week. I'll be here Wednesday, but we'll see you later. It's a B-Day Friday, so Wednesday's the only other day I got.